Good morning, friends. Yesterday we discussed some aspects of closed loop system. We saw block diagram representation of open loop system and closed loop system as well. We'll just see few of the characteristics or some advantages and disadvantages of closed loop system. Yesterday we saw advantages and limitations of open loop system. We'll see the advantages of closed loop system today. Now, closed loop system, if you remember, we discussed in the last class, it has got very high accuracy because the controller modifies and manipulates the actuating signal such that error in the system will be zero. If you just recollect what this feedback control system does. See, in the open loop system, this feedback loop will not be there. There will not be any signal that is sensed and compared. But in closed loop system, you have a feedback, a sensor will be placed inside the process of the system and it will be giving the actual value of the controlled output and it will be compared at the comparative stage. And it will be compared with the set value. And whatever is the error signal, that is manipulated and that is given to the process. And this process continues till the error becomes zero. And that's what this advantage says. It has got very high accuracy. It controls the parameters, the output parameter so accurately because constantly it is monitoring and manipulating the actuating signal in such a way that the error in the system will be zero or the desired output is constantly maintained. This sense environmental changes also as internal disturbance and accordingly modifies the error. If you recollect, in open loop system, they don't have the ability to adapt to the environmental changes. As per the calibration, as per the timer set, it will keep on giving the output and controlling the output. Okay, but in closed loop system, whether it is process oriented disturbance, whether in the furnace the door is opened and the temperature is dropping, because of that, it will automatically adjust the controller output so that the system parameter is maintained. But in addition to that, even if there are environmental changes, the ambient conditions have changed, that also your closed loop system will take care and accordingly modify the controller output so that the desired output is maintained. If you take the case of the room heating system, let us say, the room heating system we discussed in the last class, if the outside temperature is sub-zero temperature, the inside room temperature is maintained at maybe around 20-25 degrees Celsius value. But if the outside temperature is suddenly increased, then in that case, the system has increasing the output. Okay. There is some disturbance. We'll try to eliminate that. Yeah. Somebody. Pradyumna, please mute yourself, please. There is some disturbance. Pradyumna, please mute your mic. Okay, so your closed loop systems sense the environmental changes and take it as an internal disturbance and accordingly modifies the error signal and correcting signal. There is reduced effect of non-linearities and distortions. Now, this is also a very important aspect. Now, let us quickly discuss what is this non-linearity. In simple words, non-linearity is non-proportionality. Now, what is this proportionality? What do I mean? If you take the case of a simple, if you have got in a room, you have got a fan and you have got a regulator. Now, when I turn the regulator clockwise, right, slowly, that it's nothing but a dimmer, the variable resistance device. When I increase it, when I rotate it in clockwise manner, proportionately the fan speed is increasing, isn't it? So there is a linear relationship between this resistance change and the speed of the fan. Now, if the resistance is stuck up somewhere, there is no consistency in the resistance. What happens? The resistance values over some length is more or less. What will happen? I expect that I am rotating the knob by 30 degree. I expect the fan speed, this much fan speed, right? And if I rotate it further, if the fan speed starts reducing, or if it doesn't increase to the expected value, so there is no proportionality between this resistance change and fan speed. So this is somewhat similar to a non-linear behavior, non-proportional behavior. Similarly, in the case of a furnace temperature control system, I increase the heater input. I increase the heater input by some value, and I expect the temperature change to be so much, and there should be proportionality. 10% increase in heater input, I should get maybe 10% increase in temperature. I make 20% increase in heater input, I should get 20% rise in temperature. This is the expected proportionality. This is the expected linearity. But in the case of a heater, if there is leakage from the walls, so even if I am increasing the heater input, the door of the furnace is open, I might not get the proportionate increase in temperature inside the furnace. So there is a non-linearity also. So even such non-linearities and distortions in the signals, your closed loop system can take care of. This is the very biggest advantage of closed loop system. Bandwidth of such system or operating frequency zone. What is this bandwidth? Operating frequency zone for control systems is very high. Whereas for open loop systems, it is very low. It does not work in a broad range. So bandwidth of such systems is very high. Operating frequency zone of the closed loop system is very high. Some disadvantages: these systems are complicated and time consuming from design point of view and hence costlier. Due to feedback, system tries to correct the error from time to time, and tendency to overcorrect the error may cause oscillations. Now, last class we discussed this aspect, taking the classroom teaching as an example. If I'm constantly, if I'm not taking any feedback in the classroom, I'm just delivering my lecture. The system, the lecture runs smoothly, and the teacher also is least bothered whether the student has understood or not. And even the students don't bother whatever this teacher is telling. It is comfortably going. The lecture is going very nicely. I completed 40 odd lectures. Nobody has understood. I'm least bothered. It's an open loop system. But if it is a closed loop system, I will constantly nudge you and ask you whether you understood it. If I make you stand up and come on, answer me this. And good. From teaching learning process point of view, it is good. But the entire harmony of the class, the entire stability of the class is disturbed to some extent. There are small stoppages in the lecture, but it is required. I do believe that the teaching learning process has to be feedback oriented. But to some extent, maybe the teacher is not in good mood. He'll just try to overcorrect. Okay, because of some reasons, that boy that you have made him stand up is sincere, but on that day he was a bit disturbed. But because of my teacher's own mental state, he will just bang him in and just get out from my class. And so he tends to overcorrect. It's a crude example, but it should make you understand the concept of this overcorrection. And the system stability is disturbed. So this may cause oscillations in the system. So taking the case of, let us come back to our furnace control system case. The temperature has dropped inside a furnace, so the feedback, the sensor will sense the temperature as a feedback signal, compare it with my set value of 1000 degree, and it will tend to try to correct. And because of there is some time lag between the sensing signal and correction, it might so happen that there is overcorrection and the system temperature will keep on oscillating. If I set it for, let us say, 1000 degrees Celsius, it will keep on oscillating to 1050 and 950 because of this constant correction. So this is one of the drawbacks of feedback control system. So let us go to the applications of. We already seen some applications. Human being is the best example of feedback control system. Suppose I want to write something on the board. My brain makes a decision. My brain is a controller, and hands are my actuators. I go to the board and write something, and my eyes work as feedback. Instead of writing on a wall, I write on the board properly, because if uh, my brain has given me a signal, I'll just move towards the board, and instead of writing on the board, I'm writing on the maybe a wall. So my eyes sense that signal and give the brain gives the correcting signal. No, move towards left and right on the wall. So this is one of the examples. Desired position of the hands, and eyes give me the feedback signal, and it is compared in the brain itself, and the brain takes a corrective decision and sends signal to your neuromotor system to the hands, and you move your hand as per your requirement. So like that, human being is the best example. Initially, I told you it has got temperature control system, it has got breathing control system, it has got digestive control system, and most of the human body control systems are autonomous and closed loop control systems, and that's why the whole universe is working in harmony. Okay, the human body is the best example of closed loop control system or feedback control system. A second example, home heating system, though it is relevant to Western countries, and if it is heated by maybe few gases, let us say, or maybe steam. So you have got a heating system as a system. So house temperature is sensed, and it is to be maintained at 25 degrees Celsius. That is my desired output. Desired temperature is 25 degrees Celsius. Actual temperature, let us say, is presently as sensed by the temperature sensor is maybe 15 degrees Celsius. So 15 degrees Celsius will be compared with set value of 25 degrees Celsius. So error of 10 degree Celsius. So accordingly, the error signal will be generated, and the wall will be actuated accordingly, and more steam or maybe flue gases or hot air will be allowed inside the room, and this room will be heated by this hot air till the temperature becomes 25 degrees Celsius. So this is one more example of a feedback control system or closed loop control system. DC motor speed control system or DC motor drives, we have seen some of the electrical drives in our unit number 3. So DC motor speed control system, we have studied the desired speed, actual speed of the DC motor, set speed, maybe 1000 degrees Celsius, 1000 RPM is my set speed, desired speed. And you have the error signal generator, there is a comparator, error signal is generated, that error signal is amplified, and the armature current is altered if it is an armature controlled DC motor. We also see field controlled DC motor, we have seen armature controlled DC motor. If the armature current is accordingly altered, and then the motor output shaft is connected to the load, maybe electrical load, maybe some mechanical load, it is connected to some servo motor actuating valve, and that is the load, and the actual speed of the motor will be altered. Now, if the present speed of the motor is maybe 900 RPM, and my set RPM is 1000 RPM, so 900 RPM will be sensed by the tacho generator. Tacho generator or tachometer is my sensing element or my feedback element. So that signal will be sensed as 950 RPM, which will be appropriately converted into the working signal or the control signal. It will be normally electrical signal. This tacho generator will convert that RPM signal into electrical signal. Maybe 100 RPM corresponds to 1 volt, so 1000 RPM corresponds to 10 volt. So 950 RPM is the present speed of the output shaft of a DC motor. So 9.5 volt will be generated by this tacho generator, and that will be sent to my comparator. So desired speed, which will be appropriately converted corresponding to 1000 RPM, it is 10 volt, and corresponding to 950 RPM, it is 9.5 volt. It will be compared. 10 volt minus 9.5 volts it will be plus 0.5 volts, that will be amplified, and accordingly the armature current will be altered, and the motor speed will be increased to generate more torque, and this will be increased till it becomes 1000 RPM. How you're going to assess whether it is 1000 RPM? till the sense signal becomes equal to 10 volt. Okay, so when a set value is 10 volt, the feedback value is 10 volt, it is zero error. So till this error becomes zero, this feedback control system or closed loop control system will keep on repeating the cycle. So these are the few examples of closed loop control system. Let us move further. We'll see the basic elements. Now, there is one question on basic elements of closed loop control system in the exam. So we'll discuss it in the next class also because we are running out of time. So it's a generalized block diagram of a closed loop control system. Okay, so what is the basic element? You have the process or system, you have measuring element or the feedback element, you have controller element, you have control unit, correction unit, actuating unit, then processor, you have controlled variable, your feedback variable or measuring device, then you have a comparison element. So you have reference input compared with the feedback value. Whatever is the error, that error will be suitably modified, altered, manipulated so as to suit the actuating actuators. Okay, so control unit will make a decision regarding the corrective action, and corrective action will be taken by the actuators, and the process parameters will be controlled. So these are the few basic elements. In next class, we'll try to understand each of these elements in bit of details, and then for a given system, actual physical system, we'll try to identify what are the functional elements, what are the functional control elements, what are the functional correcting elements, what are the functional system or process elements, what is the functional reference input element, what is the functional control variable, what is the functional feedback element or measuring device. This we'll discuss in the next class. I think we will stop for today.